So good evening, one and all. We are starting our session on 3D graphics on behalf of the IEEE Signal Processing Society, SB chapter of NIT Calicut. I welcome our resource person, Mr. Abhishek Rhisheekesan. He is a founder and CEO at aiRender Technology Pvt Ltd. aiRender Technology is a startup working on the next leap in video conferencing. Mr. Abhishek completed his bachelor's in Electronics and Communication Engineering from NIT Surat in the year 2003 and master's from Arizona State University. He has been awarded the Outstanding Graduating MS Student in Computer Science. Previously, he was Engineering Manager in Graphics Architecture Labs at Intel. He was one of the recipients of the second highest technical award at Intel for his contribution to 3D graphics performance analysis. He holds 3 US patents in 3D graphics architecture and 4 ACM and IEEE publications. Over to Mr. Abhishek for the presentation. Thank you.
Thank you, Subodh. Good evening, everyone. Thanks to the IEEE chapter of NIT Calicut for providing me an opportunity to take you to the exciting world of 3D graphics. Thanks a lot to respected HODs of the different departments and the faculty of NIT Calicut, the institution's IEEE chapter, and the students of NIT Calicut for attending this talk. And a special thanks to Professor Abhilash and Subodh for organizing the talk and providing me with an opportunity to address the scholars at NIT Calicut. Thanks again, Subodh, for a generous introduction. So as Subodh mentioned, currently I am the founder and CEO of aiRender, and we are building a 3D video conferencing product. aiRender, the startup, is part of a startup incubation program, Venture Doubles, at Arizona State University in the US. And as you see here is our website and working video conferencing and web app link. Please sign up and give it a try. We have internship opportunities available, and I will talk about it towards the end. Now, here is the agenda. Let's probably skip to the agenda and get to the slides. Our universe exists in multiple dimensions, possibly more than 10. An average human being can perceive the world around him or her in three-dimensional space. Most existing computer applications visualize the space in 2 dimensions. In the last century, with the introduction of computer-generated graphics, many applications have started visualizing the world in 3 dimensions. Today, we are going to take a walk through the world of 3D graphics. Have you ever wondered how 3D games like Pokemon, Counter-Strike, City Racing, and Fortnite work? How do popular 3D software like Maya, Unity, AutoCAD, they bring 3D objects, models, and 3D world into action? A 3D game or a 3D world scene can be considered like a movie, which is arranged as a deck of cards or deck of frames or images and played in a sequence. Now, each frame is constructed by converting a world modeled in 3D to a corresponding 2D image, a process we call as rendering. As an illustration, let's take a look at the rotating cube on the left side. Rendering basically converts the view of the cube from a particular angle and projects it in 2 dimensions onto the computer screen, as shown on the right side. Now, in this section, we are going to get introduced to 3D coordinate geometry. Let's take a look at a simple 3D example at your home. Here is a typical dining table. You can see the shape of the dining table is made out of multiple rectangles. For one of the rectangles shown on the previous slide, as part of the dining table, let's now define the coordinates. The rectangle has a length of 2 units and a width of 1 unit, and the rectangle can be split into 2 triangles. One of the triangles has the following coordinates in XYZ coordinate space: 0, 0, 0, 0, 1, 0, and 2, 0, 0. And similarly, all the coordinates of the table can be defined. Now, in this section, we will introduce you to different spaces and the concept of transformations in 3D graphics. Primarily, there are 5 major spaces and 4 major transformations in 3D graphics. First of all, there is local space, which deals with creation of local objects. Then comes world space, which positions multiple objects in a 3D scene. Then we have the view space, which sees the world from a viewer's or camera's point of view. We'll discuss about these spaces in the coming slides, but further on, there is clip space, which clips the portion of objects to be shown in the screen and adds perspective projection. Finally, there is screen space, which maps normalized clip space coordinates to a pixel on the screen, as the screen that you're seeing here, right? For example, let's say 800 cross 600 screen. Let's touch upon the first 2 spaces and the transformation between them first. Think of local space as the 3D coordinate space in which a single object is created. For example, the tabletop in the example we showed in the last section is a local object in the shape of a cuboid and can be defined with its own 3D space with its XYZ axis and origin. Similarly, a table with the tabletop and its 4 legs and an almirah, as shown here, can be considered to be part of the world space in a specific 3D scene, where they are defined within a common global 3D space with a common set of origin and XYZ axis. The model matrix, which transforms local objects from its individual local spaces to a common world space, consists of transformations like translation, scaling, and rotation of vertices of these local objects. Now, let's see what a 3D transform consists of. A 3D transformation is essentially a matrix to vector multiplication. The transformation matrix is a 4x4 matrix. The vector contains a 3D attribute of a vertex of an object, for example, XYZ geometric coordinates. The vector is 4-dimensional or can be considered as a 4x1 matrix for all practical purposes. Now, the 3D transformation performs a dot product matrix vector multiplication of the 4x4 transformation matrix with the 4x1 3D attribute vector shown here to obtain a 4x1 transform matrix as shown on the right side. And the same transformation is generally applied to all vertices of an object. The model matrix mentioned in the last slide performs a translation, rotation, or scaling, or a combination of this for all vertices of an object in a local space to transform it to the global world space. When you apply a combination, basically multiple such transformations are applied to the same set of attributes. Now, here is a quick practice example. Subodh, can you initiate the poll survey, please?
Yeah.
So while he's initiating that, let me walk you through the example. So here is a tabletop in 3D, and you're seeing that from the top view, the same tabletop that you see in one of the previous slides. We are trying to rotate it by 30 degrees plus 30 degrees in Z-axis or XY plane as shown here. Identify the missing transformation matrix element A below as shown in this equation for vertex with coordinates 2, 1, 0, and 1 is for the perspective projection here. So it's an angular rotation. You are rotating it by 30 degrees, right? And the parameters for rotation mostly are filled up in the transformation vertex, and one parameter out here is missing, and the resultant transformed vector is given. And here are the options. The option 1 is cos 30, second one is sin 30, third one is tan 30, and fourth is sin 60. Yeah, over to you, Subodh.
Yeah, I have claimed the presenter role actually. I will show the slide and the polling together.
Yeah, I think most folks have gone for option B, sin 30, which is the right answer. Thanks again, folks, for participating in the poll. Hope that was interesting. Folks, hope that gives a perspective on how to do rotation using 3D transformation matrices. In this case, you are doing that for a vertex coordinate, one of the vertices of the one of the triangles in the rectangle 210, and this is a rotation in XY plane or in Z-axis. For let's say X-axis or Y-axis rotations, you might just move around this cos theta, sine theta, minus sine theta, cos theta, these parameters around these points for different sort of transformations in different planes corresponding to the axis. So the objects in the world space can be viewed from different angles. For example, we can place the camera on front, top, bottom, or sides, or at specific angles. Here you can see the top view of the two objects after transformation to the view space. View space is also called as eye space or camera space. Now, viewing the exterior through a window can best explain the transformation from view space to cliff space. This is similar to placing the objects in view space into the rectangular window of the world visible through a computer monitor. Some objects like the boundary wall in the picture shown here gets clipped, as you can see. Some of the plants which falls within the boundary of the viewing window is included within the clip space and are shown completely as shown here, while some of the other objects like the gate and the kennel on the left and right sides of the viewing window respectively get discarded. Screen space converts clip space objects to pixels on the screen. The screen may be of the resolution 1920 cross 1080 pixels for a laptop like this, or 480 cross 900 pixels for a mobile phone that many of you might be holding. Now we are going to view orthographic and perspective projections and frustum in this section. To understand orthographic projection, let's consider Bombay-Pune Expressway and viewing it from a helicopter or a drone. For most part, one of its lanes appears like two parallel lanes at both sides of the road, both sides of the road for a straight stretch of the road. Now this is an orthographic view of the road. Typically, orthographic projections are done for faraway objects. The orthographic frustum view shows near plane and far plane to each other, and most importantly, parallel to each other, and most importantly, similar sized in terms of what can be viewed within it. Think of near plane as a computer monitor and far plane as the plane, including the farthest object you can see within the scene, and parallel to the computer monitor screen or the near plane. The planes are near and far with respect to the viewer's eye or the camera position. The space between the near plane and the far plane is called a viewing box. The viewing box of orthographic projection is, as you can see, it's a cube-like frustum box. As you see here, the objects which fall completely within the viewing box, like the green cube, is completely visible and included in the view. The red cube which falls outside the view box is discarded, and the blue cube which falls on the boundary of the viewing box is clipped. Now here is a perspective projection of the same lane from Bombay-Pune Expressway. Now if you stand on the lane and view this far stretch of the straight road, as far as you can view, the two edges of the road seem to merge towards the far stretch as shown here. The distance between the edges seem to be wider towards you and seem to be closer towards the far end of the road. This is a typical example of a perspective projection and takes a real life perspective view of the scene. If you have gone to drawing competition for small kids, you can see most of the pictures, be it roads or houses, are drawn as orthographic projections. Most of the engineering drawings are orthographic projections, whereas the great paintings of Da Vinci or Raja Ravi Verma capture perspective projections. For that matter, like engineering drawing was one of my favorite subjects during my BTech. And okay, farther objects in orthographic projections seem to be same size as nearer objects, and that creates a weird view of the scene. Now, let's stand in awe of the simplicity of the frustum view of the perspective projection. Many of you might have already seen this. Again, the laptop screen can be considered as the near plane, and the plane containing the farthest object in the scene can be taken as the far plane. The length and height of the far plane seems larger than the near plane. The four sides joining the far plane and near plane are trapezoidal in shape, as you can see. Here again, the objects within the view box, or clip space volume as it's called, like the blue cube, is captured inside the view, inside the viewing box. The ones on the boundary, like the red cube, are clipped, and the green cube outside the frustum view is discarded. There are three parameters that define a camera's viewing direction. Imagine a fighter plane. Consider the X, Y, and Z axis of the plane as shown in the figure. The rotation about the Y axis and in the XC plane is called yaw. And the rotation about the X axis and in the YC plane is known as pitch. And finally, the rotation about the Z axis and in the XY plane is known as roll. The rotations can be in clockwise or anti-clockwise directions. Similarly, a camera can be rotated along this axis and positioned for a particular view of the scene with specific yaw, pitch, and roll parameters. In this section, we are going to take a deep dive into depth. To understand depth, consider a chair that's behind a trolley bag or a paper on top of the chair as shown here. A portion of the chair that's behind the paper or the trolley bag will not be visible and hence doesn't need to be rendered. The structure we use to record the depth of different objects to check which object is in front of the other object is called depth buffer. The depth buffer has values ranging from 0 to 1 for all pixels on the computer screen as shown here. Now 0 represents the near plane corresponding to the objects that are closest to the camera, and 1 represents the far plane which relates to the objects that are farthest in the scene from the eye view. So an object X which is in front of an object Y will have a smaller value of depth versus Y in the range 0 to 1.0. Before you receive any objects to render, all values in the depth buffer are initialized to 1, setting them as farthest in the scene. Now, in a previous section on Introduction to Coordinate Geometry, objects are shown to be built from multiple triangles. Depth corresponds to C coordinates of vertices of triangles. Let's consider a triangle from the upper left half of the chair, as shown here. Imagine a rectangle covering that triangle with its sides parallel to the length and breadth of the computer scene. For sake of simplicity, assume all vertices of the triangle have a depth value of 0.8 corresponding to their z coordinates as shown here. Now, so this triangle passes the depth test and corresponding locations in the depth buffer are marked as 0.8 as shown here. These locations map to the imaginary rectangle covering the triangle as shown here. Depth test pass means this chair triangle will continue through further steps of rendering. Now comes the triangle from the trolley bag towards its bottom, which doesn't overlap with any portion of the chair. So this triangle also passes depth testing, similar to the previous one, and respective locations in the depth buffer are marked with its depth value of 0.5. Now let's consider a triangle from the chair that overlaps with the trolley bag towards the middle of the scene as shown here. Since this triangle is the one to reach depth testing first, it passes depth test and mapping locations in the depth buffer are marked as 0.8. And here comes a triangle from the trolley bag, which overlaps with the previous triangle from the chair towards the middle of the scene. Note that the depth of the trolley triangle is 0.5 and it's less than 0.8 depth of the chair triangle. So it passes the depth test and mapping locations in the depth buffer are overwritten with its depth value of 0.5. Now, on the other hand, assume the same trolley triangle came for depth testing before the middle scene chair triangle. It passes depth test and the depth buffer locations are marked as 0.5. Since the chair triangle came for depth testing after the overlapping trolley triangle, it fails depth test as its depth is 0.8 and higher than trolley triangle's 0.5. The chair triangle is discarded from further rendering through the rest of the pipeline. Okay, now comes stencil and face culling. We all have played with stencils, as in the stencil used by many of you when you were kids. Stencil is pretty much same as the stationary stencil that most of you have used in our schools, and typically it's used for showing alphabets and numericals in a 3D graphic scene. And at the same time, ensuring the background 3D graphic scene is rendered without any disruptions. Let's take a real life example of a 3D graphics game that utilizes stencil. As you can see on the left bottom corner, the player one Lakshman is being shown using stencil. Here the alphabets in Lakshman are sort of carved out using stencil and the background 3D graphics scene of the game is visible through the letters, while the box containing the alphabets of Lakshman occlude the background 3D scene. Similarly, stencil is used to showcase the options of different guns for the game player and the score as shown on the top right corner. Stencil testing is implemented using stencil buffer. It's similar to the depth buffer shown in the last session. Stencil values of 0 to 1 are used in stencil buffer to indicate whether or not to render each pixel on the screen based on a stencil mask, which we will shortly introduce in the next slide. All values in the stencil buffer are initialized to 0. And here is a stencil mask which shows the letter L in Lakshman. As you can see, the locations in the stencil buffer mapping to the portion of the 3D graphics game scene visible through that region of the alphabet L are marked as 1, indicating its visibility. At the same time, the stencil buffer locations mapping to the brown box covering the stencil mask for letter L are all set to value of 0, which indicates the mask will be occluding or covering the background region. That's pretty much the world of stencil testing. And now we will see the dark side of backface culling. The most popular face culling method is backface culling. There are several other methods also in culling, but let's go through this. Consider the tabletop that we had seen in the prior sections. If the viewer of the camera is seeing the tabletop from the top view, the top face of the tabletop is visible and the bottom face of the tabletop is not seen by the viewer. The top face and the bottom face of the tabletop are rectangular in shape and are made up of two triangles each, as discussed in the previous sections. In order to perform backface culling, we assign a winding order to the vertices of each triangle. From the exterior of the tabletop, vertices of all triangles are numbered incrementally in a counterclockwise direction. The vertices are numbered in counterclockwise direction as if the triangle is facing U. As you can see, the vertices of one of the triangles on the top face of the tabletop are numbered from 1 to 3 in counterclockwise direction. Similarly, the vertices of one of the triangles on the bottom side of the tabletop are numbered from 4 to 6, 4, 5, 6 in counterclockwise direction. If you assume the triangle is facing you, in this case from the bottom side, it would look like counterclockwise, whereas here it is shown as clockwise because you're showing this from the top side, right? But ideally you would be viewing it from the bottom side. So when you view from the top, the winding order of the vertices of the bottom face triangle becomes clockwise. Now all triangles with clockwise winding order are culled, and the rest of the triangles with counterclockwise winding order are retained and are visible. This section, we are going to delve into one of the most important topics in 3D graphics rendering called rasterization. Most of you may be familiar with the raster scanning methods that you have seen in older televisions. As we have seen in one of the earlier sections, 3D objects are made from 3D polygons, and 3D polygons are made from triangles, which are the basic building blocks of 3D objects. As you can see here, the tabletop is a rectangle, which is a polygon, and it consists of two triangles. Rasterization, in essence, involves converting triangles of 3D objects in the 3D scene into pixels on the computer screen. The basic requirements for rasterizing two adjacent triangles, that's triangles that share a common edge, involves: one, it should not leave any holes, that's non-rasterized pixels between the two adjacent triangles, so that the rasterized area is completely filled. Two, no pixel is rasterized more than once, that is, the rasterized triangles should not overlap. In order to achieve these requirements, certain rasterization rules are established. One set of such rules is top left rule. It states that a pixel is rasterized if and only if its center lies completely inside the triangle. Or two, its center lies exactly on the triangle edge, that's either top or left edge. In case of corners, the pixel center lies exactly on the multiple edges, that is top or left edges. As you can see here, a top edge is exactly horizontal and lies above other edges, and a left edge is a non-horizontal edge that is on the left side of the triangle. Here is a left edge and here is a top edge. As you can see in the figure, this red edge in the triangle on the left side, that's the left edge, and the red edge in the triangle on the right is the top edge. Now let's go through a rasterization algorithm. In order to reduce the number of pixels that need to be traversed as part of rasterization for each triangle, the algorithm computes a bounding box for the triangle to be rasterized. Computing the bounding box involves finding the minimum and maximum x and y coordinates of the three vertices making up the triangle in raster space. You can see how they are getting the x minimum, y minimum, and the x max, y max in this diagram. Once you compute the bounding box of the triangle, the next step is to iterate only over the pixels within the bounding box to rasterize the triangle, rather than rasterizing over the entire set of pixels on the computer screen. Rasterization checks whether each pixel in the bounding box is inside or outside the triangle using the rasterization rules that we discussed in the prior slide. As you can see, it's walking from the from the left to right and then right to left within this bounding box, and then it's trying to see which all pixels are lying inside the triangle and which are lying outside the triangle. Now this section helps you learn how to sample texture maps. First of all, let's see why do we need texture sampling. Let's take an example of a high quality 3D space, 3D face like the one shown on the right side. A typical high quality 3D face requires anywhere between 40,000 to 60,000 vertices or more. If we were to color each vertex separately, it requires an RGB color value per vertex amounting to around 40,000 to 60,000 RGB color values. Now that takes a lot of space in the memory to store these values. Instead, let's consider a texture map. Think of texture map as a blanket wrapped over the 3D object. For example, consider the tabletop shown below. We can wrap it with the texture map of plywood texture as shown here on the right. Now, typically, texture maps are stored as a single image or multiple images. Here, the plywood texture image is shown on the right and has a width of 400 pixels and a height of 200 pixels. The texture coordinates in the axis along the width or the x-axis are typically called u coordinates, and the ones along the height or y-axis are called v coordinates. UV coordinates, as you can see here, are scaled from 0 to 1. Now consider the top facing part of the 3D tabletop object that we have seen in the prior slides. The rectangular tabletop can be split into two triangles, and the XYZ coordinates of the vertices of the triangle are as shown below. Now, the vertices of the top right triangle are mapped to UV coordinates in the plywood texture image as shown here. For example, the top right corner vertex with XYZ coordinates 210 are mapped to a pixel location with UV coordinates 0.8 and 0.9 in the texture image, and the corresponding RGB value of that pixel is mapped to as the color for that vertex. Similarly, other vertices of the triangle can be mapped to different UV coordinates in the texture image, as you can see here. The advantage with storing such a texture map is that it can be reutilized for texture mapping the same person's face in different scenes in a 3D graphics application. Now, the coming section, we will introduce you to the concept of shaders in 3D graphics. Before going into shaders, let's see how a typical 3D graphics pipeline looks like. A 3D graphics application is fed by the game programmer or the graphics application programmer to the 3D graphics pipeline, which is implemented in both software and hardware. Different blocks in a 3D pipeline are shown here, and we have already gone through most of these blocks in detail in prior sections. For now, we'll focus on vertex and fragment shader blocks as shown here. Each block in the pipeline has a specific function, like the rasterization or texture mapping that we have explained in the previous sections. Some of these blocks are programmable and can be customized by the game programmer, like the vertex shader and the fragment shader. Mostly, the vertex locations and the pixel colors of each vertex and each pixel are independent of other vertices and pixels, or only dependent on the neighboring vertices or pixels. So the vertex and fragment shaders are highly parallel small programming blocks. Now let's see what's a vertex shader. It primarily performs transformation of XYZ location coordinates or other attributes like normals of vertices of triangles in a 3D object. It performs rotation, translation, or scaling, zooming, or other similar transformations of the triangles. The transformations of triangles and its vertices were discussed in one of the previous sections. The diagram here shows the rotation of the vertices in a triangle. Vertex shader takes the 3D XYZ coordinates or other attributes of a single vertex as its input. Similarly, the output of the vertex shader consists of the transformed 3D coordinates or vertex attributes of a single vertex. The primary function of a fragment shader or pixel shader is to determine the final color of a pixel. The input to the pixel shader is the initial color of a single pixel. For example, it can be the color of the nearest vertex to the pixel, or it can be fed with a uniform color for the entire triangle. The input pixel is obtained after rasterization of triangles to pixels and possibly after depth and stencil testing as shown in the diagram on the right. The output of the pixel shader is the final color of the pixel as shown in the diagram of the rasterized pixels of a triangle on the bottom right. The pixel shader may run lighting algorithms or shadow algorithms, which can be seen in detail in future sessions. Now, when coming to lighting, lighting in 3D graphics is a comprehensive topic in itself. If you like this session, we can plan for a session on lighting related topics in the future. As you can see here, here is a YouTube link for the 3D graphics topics covered in today's talk. Please do check it out. Now at aiRender, we are building an AI-based real-time live streaming in thin air 3D video conferencing solution, Hi 3D Meeting, for greater reality. Here is the secret sauce behind our product. 2D videos of video conferencing participants are captured using cameras associated with devices like mobile phones in your or the handsets in your hand, right? Or an AR/VR headset. And the 2D image frames in the captured video stream are converted on a real-time basis to lifelike 3D graphics models using our AI engine called AirBrain, sitting on the cloud. The 3D graphics streams of video conferencing participants are displayed in thin air using holographic displays or similar displays on AR/VR headsets. Now, to provide a sneak peek into how much we have progressed so far, we have a web-based Hi 3D Meeting video conferencing app ready. As you can see on the left, showing my 2D video and the corresponding 3D video during a call. The underlying AI engine, AirBrain, is also ready, as shown here on the top, converting my teammates' 2D video to 3D. As shown in the video below, we have launched Hi 2D video conferencing app, which is a precursor to the 3D meeting launch. We are part of Venture Devils, a startup incubator at Arizona State University. We have internship openings for 4 profiles primarily. One of the profiles is on machine learning or neural networks based on 2D to 3D reconstruction of human faces. Then we have a profile on 3D graphics rendering using game engines like Unreal Engine and WebGL framework to enable 3D rendering of 2D to 3D reconstructed videos of human faces. The next one is full stack mobile and app development for video conferencing apps. And there is a profile in business development where you get a first-hand experience in marketing, sales, finance, operations, market analysis, and competitive analysis. The internship candidate for 2D to 3D face reconstruction will be working on machine learning algorithms, neural network algorithms to be specific, to improve the quality of human faces using CNN and GAN and associated loss functions, 3D specific loss functions, and add reconstruction capabilities for the backside of the human face, teeth, and human body, and to improve the speed of inference and training. 3D graphics rendering intern candidate will be working on developing a 3D engine to render human face real time using Unreal Game Engine and WebGL based JavaScript APIs from 2D to 3D reconstructed videos of human faces obtained from our Hi video conferencing app and AirBrain 2D to 3D machine learning engine. Mobile app or web development internship candidate will be working on full stack development of video conferencing web app and Android or iOS mobile apps using React, JavaScript, HTML, CSS, and an open source video audio communication framework called WebRTC, which is based in C and JavaScript. The business development intern will be getting a first-hand experience in marketing, sales, market analysis, competitive analysis, in preparing investor pitches, customer pitches, in projecting company-related financial requirements for investor pitches, and in driving social media campaigns and outreach. Thank you all, and now we can open the floor for questions from the audience. Yeah.
Sir, I'm a faculty here in MED, and I teach students CFD, Computational Fluid Dynamics. So in that, the foremost step is discretization, and we have in computer science something known as abstraction. So which we come from some dedicated to from specific to infinite. So I see your this attempt of going from a two-dimensional snap or clippings to a three-dimensional clipping as some sort of abstraction. What is your opinion about it?
When you say abstraction, can you elaborate a little bit more? What sort of abstraction? Can you give me an example, maybe?
Sir, abstraction means what can I say? Say means suppose we have a line. Okay, a line can very well be defined by its two endpoints, and if we have the slope, we know everything about that line, and there are infinite number of points. So what we have done is we are moving from two the information of 2 points is enabling us to talk about or take to an infinite space, and that is what we do discretization. When we do discretization, we come from an infinite space where the governing equations are there, and then we come to the finite space, finite computational space, the grid and all those things. So but because from you because three-dimensional, obviously three-dimensional figures images have third dimensions also, whereas two dimension have only two dimensions. So in that sense, it is an expansion of the dimension. So in that sense, we can say that it is coming moving from a specific to a generalization.
Specific to what was the last part? Sorry, I didn't.
Generalization.
Generalization. Okay, okay. All right. So here, as you can see, right, there are the red box, red cube over here is clipped, right? This is one of the scenarios you were referring to when it were mentioning the clipping part, right? It's not an infinite space that we use here. We have a near plane and a far plane, which is well defined essentially. So we are not going to show, let's say you are looking through the window. You're not going to show something that's beyond your normal view or beyond whatever is needs to be shown in the scene, something that's farther, right? Maybe 2 kilometers away, right? Maybe you are not going to show that. Whatever is visible through that view, right? Towards a certain extent, right? Distance from the camera or the person's eye view, right? You're going to define a far plane up to which you will show all the objects. Similarly, out here, it would be the computer laptop screen, right? Or the which basically you would take it as the near plane. So whatever objects lies inside, we will include that. Whatever is outside, we will discard it. Whatever is lying on the boundary, we will clip it. And it's not specifically related to abstraction. It's a mathematical method. So you see the intersection points on this particular object, and typically objects are represented by triangles in the 3D space, as I was mentioning in one of the prior slides, right? So this is a cube. So each side, 6 sides are there. Each one of them have 2 triangles. You see a triangle is, there is this frustum and the trapezoidal shape of the frustum, and so the boundary lines are there and the boundary planes are there, right? So you see the points of intersection between a triangle, and you see which all, okay, so it might intersect on 2 sides of the triangle, right? Or maybe on one vertex of the triangle, or maybe one edge of the triangle, right? So based on which you can determine which side of the triangle lies on the left and which side lies on the right, or which side is included within this frustum box and which side is outside, right? So now let's say it's a equilateral triangle, right? And you are intersecting 2 of the sides, right? Not the base. Right. So basically, there would be a triangle formed at the top, and there would be like a trapezoidal shape at the bottom. That trapezoidal shape will be again converted into another 2 set of triangles. So that's what we do. So whatever, let's say the trapezoidal shape is inside the box, right? It will be converted into two triangles and it will be used and it will be shown that portion of that object, which includes the trapezoidal part, will be shown. So this is what we use for clipping. Hope that clarifies it.
Okay, sir. Thank you so much, sir. Thank you.
Yeah.
So we have a couple of questions in the chat box. Sushmita has a question. She's asking, what are the on which programming language are you working with?
So like I mentioned in the internship positions, right? So the 3D graphics rendering is done using Unreal Game Engine, which is written using C++ based APIs, plugins and APIs. The 2D to 3D reconstruction is done using machine learning frameworks and like TensorFlow, Keras, etc., PyTorch and all that. It's written in Python, as you know, and we use multiple computer vision libraries and image processing libraries. Many of them are written in Python only. Some of them might be written in C and all, which we usually port to Python. And then there is mobile app and web app development, which is done using full stack product web development or product development framework. That includes React, Redux, JavaScript, HTML, CSS, etc. And the backend side of the app, which does the video audio communication, the video audio compression, the encryption, right? Encoding, decoding of videos, etc. All that's done using an open source framework called WebRTC. This is written primarily in C and JavaScript. So these are primarily the programming languages that we use.
Okay, thank you, sir. We have another question from Nidin. He's asking, is the app still in development phase and what are the current challenges to address?
Yeah, as you can see, it's only showing the face part, right? Which is the frontal part of the face, the hair and the ears, right? And a little bit of skin here, right? But it's mostly showing that. It's not showing the teeth. It's not showing the rest of the body, right? And also it's a smooth version of myself, right? And so increasing the resolution of that 3D reconstructed 3D object or 3D face, right? Adding the tooth or the teeth to that, right? Showing the backside of the face. Now, in general, the performance improvements that we can do, for example, the speed at which you are doing the inference, right, would define whether we can do a 3D video conferencing in real time, right? Otherwise, and plus you have to also put some resource constraint. This is a product, right? We can't use like a supercomputer to do this 2D to 3D reconstruction, right? So we are using cost-effective GPU instances for this 2D to 3D reconstruction, cloud-based GPU instances. So optimization on that front, and you have to show the rest of the body, including the clothing, attire, and all that, right? So sometimes the person might be presenting something in a conference room and might be standing towards the the projector and the screen, right, towards the backside of the room, and the camera might be at the other end of the room. So you can see the entire person. So you need to show the entire person 3D. Similarly, let's say, you are moving your, so you see here the teammates video is moving pretty slowly from one side to other side. If you, let's say, move quite fast from one side to other side, we see certain anomalies in the reconstructed 3D. So we are trying to use certain algorithms to fix those gaps and all. Well, those are some of the challenges. And of course, we have our 2D video conferencing app, and it's available at our website. This is a precursor to the 3D launch. It's available at https://www.aiRender.com. aiRender.co. Please give it a try. You can subscribe to that and for free and give it a try. This is similar to like your Google Meet and other apps which show like web-based 2D video conferencing. We need to make that more robust and introduce certain features that are going to give us a edge over existing competitive products. And yeah, the 3D rendering needs to be done in Unreal framework, and we have like a prototype working there, but then you have, in order to productize it, right, you have to do that rendering in real time, and you need to make it really fast. The rendering needs to be really fast, and it needs to be packaged in a holistic environment. It has to be an application that's available in Windows, Android, Mac, iOS, or in web-based applications, etc. So those are some of the challenges. And what else? I think that gives, yeah, and of course, increasing the resolution or the 3D face, right? Eventually, it should give a better experience than 2D video conferencing. When you see, like, let's say, Professor Abhilash or Subodh, right, in your meeting, you should be able to see the person as if you are sitting next to the person, right? It should be visible in that level of clarity, that level of resolution, right? So in order to do that, we need to improve upon the algorithms that we are using for 2D to 3D reconstruction, machine learning, computer vision, image processing related algorithms. Hope that gives a holistic picture.
Yeah, thank you. We have another query from Dimya Gopalakrishnan. She's asking, is 2D videos converted to 3D? Can 3D videos directly be captured and streamed?
Yeah, so there are scanners, 3D scanners, which you could use in order to capture 3D. I mean, usually 3D pictures or 3D frames are captured. You can possibly capture 3D videos also. But then these are extremely expensive equipments. I mean, a high quality scan, right? So in fact, one of the scans I showed here in order to explain, yeah, for example, this one, right? Or even the one used in the texture case, right? This one, this is a 2D rendered image of that 3D human face, right? So the actual 3D, it needs to show like around 50,000 vertices, maybe somewhere between 30,000 to 60,000 or more vertices in order to show a really high quality 3D scan, right? So you need to use sophisticated equipments for that. And those are like tens or hundreds of thousands of dollars worth equipment. So it's not available for mass and common people, right? Similarly, so our idea is to put this into the hands of common man. Like if you are using a laptop, right, have an integrated projector within that, which could showcase the 3D projection of the person into thin air, like holographic display sort of thingy, right? Or if you're using a mobile phone, right, you just press an app button and it will showcase the 3D projection of the person into thin air, right? But with extremely high quality and extremely high resolution, so that it gives you an experience as if you are meeting this person face to face almost.
Actually, coming to the hardware part, where does the innovation in the hardware part comes in here, or where is the focus of innovation in hardware part when it comes to 3D holographic displays?
Okay. Yeah, so we have started some work on that. We are engaging with some optics and physics professors and electronics professors in order to bring up this 3D holographic display projections. This is, I mean, if you search through the literature on this, right, it's usually done using diffraction properties of um, different elements essentially. So out here we have got a particular hardware kit, right, and we have identified a chip which could it's a MEMS based chip, and it has a lot of these mirrors which can be used, very small minute micro size mirrors, which could and we could use the diffractive properties of that in order to project the person's face, right, or the person's holistic body, including the clothing, attire, and all that, right? You can showcase the person into thin air as a 3D holographic projection using diffraction and interference-based properties. These are still in experimental stages, and
I invite Ms. Sri Lakshmi to deliver the vote of thanks.
Thank you, Subodh. I, on behalf of IEEE Signal Processing Society Chapter, NIT Calicut, and Department of Electronics and Communication Engineering, would like to express my gratitude to Mr. Abhishek Rhisheekesan for such a wonderful interactive session. I would like to extend my gratitude to Dr. Abhilash ji for organizing and making this session a great success. The session was very informative, and I thank all the participants for their active participation. And thank you, sir, once again for your valuable time.
thank you, Sri Lakshmi. Thanks everyone for attending the talk.